In this section, you are given experimental data for a reaction where a chemist has run several different trials of this reaction, and he has varied the amount of concentration for each of the reactants in order to determine what the effect on the reaction rate will be. You are asked for these particular reactions to determine the overall rate equation for the reaction, and that includes figuring out what the rate constant is. Now, there are two different ways to solve this type of problem. There is a long way and there is a short way. The author of your book uses the long way, and that's actually the way I'm going to demonstrate to you first, just to walk you through it, to help you understand it, because sometimes I know it's easier if somebody walks you through it in place of trying to read it. But then I'm also going to show you the short way to figure this out. And so if you're good at looking at numbers and recognizing relationships between them, you will be able to use the short way in place of doing this the long way, okay? So again, this is on your sample problems for the videos, the bottom half of the first page. A chemist studies the following reaction. 2NO plus Cl2 yields 2NoCl. And in order to determine the rate equation, he runs the reaction 3 different times and comes up with the following data. What is the rate equation for this reaction? Okay, so these are concentrations, so the units on all of these are molarity. This is the rate that he measures, and so this will be in molarity per second, just like we've seen before. Now, what you have to watch when you're doing this is you have to see how the reactants are changing with respect to one another. The first thing I want to do here, actually though, is to write an equation for what the reaction rate for this particular reaction looks like. So my rate is going to equal my rate constant times the concentration of NO, and I don't know what the order is, so I'm going to put an X up there, times the concentration of the chlorine, and again, I don't know what that order is either, so I'm going to put a Y up there until I get it figured out, because the first step in doing this is to figuring out what the reaction orders actually are, so that I'll then be able to figure out what the K is. Okay, so when I have 3 trials to look at, so when I'm comparing these, you are probably familiar with what a control to a reaction is, at least I hope so. That's something that likely you've talked about in science for many, many years already. So with a control, you're going to hold one piece constant while you change the other piece to see how that piece affects the overall results. So if I look at trial 1 as compared to trial 2, I notice that the concentration of the chlorine has stayed the same, but the concentration of the nitrogen oxide has doubled, and that then had a result, or had an effect on my reaction rate when that was measured. So when the 2 trials that you choose to compare, you have to be sure that there is one of the reactants is held at the same concentration while the other one changes. Now, in order to set this up, I'm going to choose one trial and start filling in the information that I know. So I also want to make sure that the one that I choose first is the one that has the bigger concentration. So this is, since this is 1 and this is 0.5, I'm going to use trial 2 first. So trial 2, if I write the rate equation for that, I know that the rate is 0.076. I don't know what the rate constant is. The concentration of the NO is 1.00 raised to some power, and I know that the Cl2, the Cl2 is 0.50, and it is also raised to some power. Okay, so hopefully you can see what I did there. This is the rate, and then these are the concentrations of my 2 reactants. Now, what I'm going to do is I'm going to say, well, I know that if I compare that to trial 1, the Cl2 doesn't change. So now I'm going to write an equation for this particular trial. So for trial 1, the reaction rate is 0.019. reaction rate's the same for both of them, but in trial 1, the NO concentration is 0.50 and raised to the same power, and the chlorine is 0.50 raised to some power, okay? Now what I'm going to do, as he explains in your book, is I'm actually going to divide these two equations. So I'm going to take trial 2 divided by trial 1. So this side divided by each other, this side by each other. And you might go, why on earth would you do that? That just looks messy. Well, actually something very interesting happens here. I should have put my units in here because this is molar, this is molar, this is molarity per second, this is molarity per second. I apologize for forgetting those. So now what you can see is that this cancels out because it's the same on the top and the bottom. The K cancels out because it's the same on the top and the bottom. And the meters per second cancels out on this side because it's the same on the top and the bottom. So now what I have isn't nearly so difficult. 0.076 divided by 0.019 gives me 4. On the other side, this looks bad, but the rule of exponents, the rule of dividing exponents, says if I've got the same exponent on the top and the bottom, I can take 1.00 divided by 0.50 and raise that to the same power, or you can split them up like this. Well, what's 1 divided by 0.5? Well, it's 2. So this is going to be 2 to the x power. Well, what power do I have to raise to 2 to get 4? 2. 2 squared is 4. So x is going to be equal to 2. So that tells me that the rate for this is 2. Now I need to do exactly the same thing in order to figure out what the order for the chlorine is. But this time, I'm going to want to cancel out the NO. So if I look here, the NO has the same concentration between trial 2 and trial 3, and the chlorine is the one that's going to change. So this time, I'm going to use, now I want you to keep that in mind because I'm not going to have enough space here. So we're going to remember and put it up here that x equals 2, and we're going to make some more space here. So this time, I'm going to start with trial 3, and the rate is 0.152. I don't know what the constant is. NO is 1.00 raised to some power x. I mean, I know that it's squared now, times the chlorine, which is 1.00 to the y. Trial 2 has a rate of 0.076. Rate constant is K. This is 1.00 to the x, and this is going to be 0.50 to the y. So I can do the same thing that I did before, and once again I forgot my units. At least I'm consistent, right? So this is moles per second, molarity per second. Okay, so what can I cancel out this time? Well, rate constants are still the same. Those units are the same, so they cancel out. This time, this piece is the same. 0.152 divided by 0.076 gives me 2. This is 1 divided by 0.5, which is 2 to the y power. Well, remember, anything to the first power is just itself, so y equals 1. So now I have figured out what the order is for each one of these. X equals 2 and y equals 1. So again, I'm going to make some more space here. Now that I know the reaction orders, now I can figure out what my rate constant is. And you can actually choose any one of the 3 trials that you want. It does not make a bit of difference because you will get the same answer no matter which trial you choose. So just for simplicity, I'm going to choose the first trial. So the first trial has a rate of 0.019. See if I can remember the units this time. Molarity per second times the rate constant K. The NO concentration is 0.50 and I know that my X is 2, and my CL is 0.50, and I know that my Y is 1, so I don't have to write the 1 up there. So therefore, when you take 0.019, you divide that by 0.5, and then you divide it by 0.5 squared, your K, and once again, I forgot my units. I'm setting a really bad example for you guys, not putting units on things. So my K, then, when you divide that out, is going to be 0.15. Well, what are my units? I have molarity. Here I have molarity squared. Here I have molarity. So when I move those to the other side, what that's going to give me is 0.15 over molarity squared seconds. Okay? So now that I know the rate constant, I can then put that into the overall rate equation, and that will give me the answer that we're actually looking for. So the rate for this particular equation is equal to 0.15 over molarity squared per second times the concentration of NO to the second order times the concentration of Cl2 to the first order. So this is your overall rate equation, and that's what you're looking for. And you're going, oh my goodness, that was a lot of work. Yes, it was a lot of work. Here's the shortcut that you've been waiting for. If you can look at these and look at the relationships and see what those relationships are in your head, you can actually skip those first two really long steps where we have to divide everything out. So let's see what that would look like. You have to start the same way where you say, okay, these two are the same, these two change. Well, 0.5 to 1, I can see that that doubles, okay? If I go from 0.019 to 0.076, now you may have to type that into your calculator if you can't see it in your head. So if you type it into your calculator and you divide that, you're going to see that that's a factor of 4. So I took this times 4 to get this. I took this times 2 to get that one. And so what that means is if this was 2 and this was 4, that means this doubled while this quadrupled. So therefore, what that means is that this has to be a factor, an order of 2, because 2 squared will give me 4. Okay? That was a whole lot easier than doing all that division, right? Okay, so now let's look at the other one. Now I'm going to compare trials 2 and 3. These two stayed the same. Change color here so you don't get confused. To go from here to here, it doubled. Yes, 0.5 to 1 is a simple multiplication by 2. It doubled. To go from 0.076 to 0.152, again, you may have to use your calculator and divide those two out, but when you do that, you see that, again, that was simply doubled. And so if it was doubled, doubling this also doubled this. So what power do I have to raise this to get this one? I have to raise it to the first power. So then at that point, once you know what these reaction orders are, then you can jump in at this step and figure out what the rate constant is. Okay? So what I'm going to do now is we have another problem to look at, and I'm only going to do this using the short method so that hopefully you'll be able to see how that one works, and hopefully we can avoid you having to do all of that other math. If you have to, it doesn't matter. You can do it any way you want. So if it's easier that way, that's fine. But if you can do the shortcut, I would certainly recommend it. Okay, so we will get this other information up here so we can both see it. So this time, our reaction is C4H, is that a 9? Yep, H9Br plus OH minus yields C4H9OH plus Br minus. And I'm just going to throw this information up here really quickly, again, so that we can see it. This is 0.10, 0.20, 0.10, and then here I have 0.10, 0.10, 0.20, and then my rates are 0.0010, 0.0020, and 0.0010. Okay. So we're going to try to do this one by inspection. That's what I'm going to call the shortcut. We're going to do it by inspection. So if I look at this, my rate equation is the rate constant times the concentration of C4H9Br raised to the X power times the concentration of OH minus raised to the Y power. So now let's look at and analyze this data. Because what I need to do, again, is I need to find two trials where one reactant stays the same and where the other one is going to change. So if I look at trial 1 and trial 2, I notice that the OH stays the same, and to go from 0.1 to 0.2, that's been doubled. Okay, what happened to the rate? Well, if I look there, from 0.001 to 0.002, that also doubled. And so if this doubled and this doubled, what power do I raise this to get that? That's going to be the first power. So the order for C4H9Br is the first order. Okay, now let's look at what happens so that I can get some sort of answer for OH minus. Here I need to compare trial 1 and trial 3, because that's where both of the concentrations for the first one are the same. Both of these are 0.1 to 0.1. So I have to use those two trials this time. So therefore, when I go from 0.1 to 0.2, that was doubled. And if I go from here to here, look what happened. There was no change in the reaction rate that time. So what does that mean? Well, if I double this reaction, double this concentration of this reactant, and nothing happened to the rate, what does that tell me? Well, it tells me that this has no effect on it, and so therefore, that means that this comes out to be a 0. It's to the 0 power. It doesn't have any effect on the reaction rate. So now, knowing that, I can just go straight in and determine my reaction rate. So I'm going to pick the first trial, 0.001. Let's see if I can remember my units this time. Molarity per second equals the reaction rate times the concentration of C4H9Br, which is 0.1, raised to the first power. And this one doesn't have any effect on it. So therefore, what this is going to be, my rate constant, if I take 0.001 and divide it by 0.1, that's going to give me 0.01, and I still didn't do it right, did I? I still forgot my molarity up there. And so this molarity into this molarity is going to give me a units of per second. So my overall rate equation is equal to 0.01 per second, because that's my K, times the concentration of C4H9Br to the first power, and I don't actually have to put that up there. Okay, so that was a little bit shorter, so if you can look at these numbers and see the relationship between them, you will be able to save yourself a lot of work. So I would like to encourage you to try it that way when you do your homework.